So let's look at standard enthalpies of formation delta H of F. Your textbook has an appendix of these types of values, and so you want to make use of them. On the test, I'll give you a reference with that particular information in it. Standard mole enthalpy of formation is the enthalpy of reaction in which 1 mole of a substance is formed from its constituent elements. That is, you form 1 mole of a compound from elements on the reactant side to 1 mole and only 1 mole of the product compound. For example, for magnesium chloride, you got Mg solid plus Cl2 gas forming MgCl2 solid, and that liberates 641.8 kilojoules, or we can say the delta H is a negative 641.8 kilojoules. Note the coefficient of the magnesium is 1 and it's formed from elements in their standard state. That is the way they'd normally be at room temperature. And those standard enthalpies of formation are good at 298.15 Kelvin and the 1.8 atmosphere. And then if it's an element, then the delta heat of formation will be 0 at that particular time. And you don't really have to look that one up in the table per se. Hess's law in its more useful form. A reaction occurring under standard conditions, the standard enthalpy change is the sum of the molar enthalpies of formation of the products, each multiplied by its coefficient in the balanced reaction, minus the corresponding sum for the reactant. So it's products minus reactants, where the n in the formula represents the stoichiometric coefficient. You say, well, what if it's not under standard conditions? Turns out delta H does not vary that much like some other thermodynamic quantities might. So you can kind of get away without too much error just using the table for delta H. That's not true of some other thermodynamic quantities, however. We'll talk more about that in the second chapter of this. So the standard mole enthalpy of formation, phosphoric acid negative 281 kilojoules per mole. So we want to write that reaction for which I produce 1 and only 1 mole of phosphoric acid in its standard state. So we'll have to consider what the standard state of each element is. Okay, in this problem, we wanted to write a reaction that produced 1 and only 1 mole of H3PO4 because that's the heat of formation reaction. So if you're asked for that reaction on a test, you want to write a reaction like this where you form 1 and only 1 mole. We'll consider that a solid. Now, what are your elements in their standard states? Okay, it turns out if you look in there, it's the P4 allotrope that is 0. You get O2 is for oxygen, and we got H2 for the hydrogen. So now we've got all their elements in the standard state, but now I need to balance it in such a way that I only get 1 mole of product, which is going to require some fractions. So if I got 1 phosphorus there and 4 there, I'm going to have to put a 1/4 there so they only got 1 phosphorus. I got 4 oxygens, so that's going to require 2 of those. I got 3 hydrogens, so I'm going to have to put a 3/2 there so we get 3, just like in our other problem. But the trick is you form 1 and only 1 mole of product. All right, so let's calculate the enthalpy change for the reaction where H2 plus 1 mole of F2 forms 2 moles of HF at 25 degrees Celsius and 1 atmosphere of pressure. This is a fairly simple one because we're forming 1 mole of a compound from the elements. Remember, the elements heats of formation from the table will be 0, so the only one we really have to look up is the HF. So next we want to start using the data from the table, and I've copied it down here so we don't have to look it up. Negative 271 kilojoules per mole for the HF. The other two are 0 because they're free elements. And we're going to calculate the heat of formation. So the standard heat for the reaction, which I'll abbreviate RXN, is going to be equal to, algebraically, 2 times the standard heat of formation for the HF, and that's the products, minus the standard heat of formation for the H2 plus the standard heat of formation for the F2. As we said, both of those are 0, so this just kind of goes away, and we're left with 2 times that. So it's going to be 2 times a negative 271 kilojoules. If you interpret the coefficients as moles, then the moles cancel, and you're just going to get an answer in kilojoules, so I'll just pre-cancel the moles out. And we call that a negative 542 kilojoules. But that's for the reaction as written. That's for the formation of 2 moles of HF, not just 1. In this next problem, we're going to look up the values in the appendix. This is the combustion propane. So this is more of a standard reaction like we've been looking at. And ultimately where we want to get is calculating this heats up reaction for a real reaction instead of some of what we have been doing. And so we'll have to look up all those but the oxygen in the table, because oxygen is a free element and it is 0. All right, so let's look at this and see if we can get some calculations. Again, I have pulled the values out of the table for you. Make sure you pull the right value, because this is water in the gas phase, not water in the liquid phase. And there's values for both in the table, so you make sure you're getting the correct one. Past that, we just plug and chug. The standard heat for the reaction equals 3 times the standard heat of formation for the CO2, doing the products first, plus 4 times the standard heat of formation for the H2O. That's your product side. We're going to go minus your reactant side, minus delta H standard formation for the C3H8. And if you want to, for the sake of completeness, you can put the heat standard formation of the O2. But since that's 0, it just kind of goes away. And we need to plug in values for the other 3. So standard heat of the reaction is going to end up being 3 times a negative 393.5 kilojoules for the CO2. Again, I'm just canceling out the moles in advance. We interpret that 3 as moles. It cancels with the moles there. Plus 4 times a negative 241.8 kilojoules. That, again, is our product side. We're going to subtract from that the reactants, which is going to be a negative 103.8 kilojoules. So minus a minus is going to be a plus. The standard heat for that reaction, then once I do all the math, is going to be a negative 2,043.9 kilojoules. And that's going to be the energy for every 1 mole of propane that burns under these conditions. We'll work one more where it's a little bit more applied. We're going to have 55.5 grams of benzene, C6H6, and we want to know how much heat is released when it is burned. So not only do we need to write the reaction, which we've practiced before, we're going to need to get the delta H of that reaction using the values in the table, and we're going to have to figure out how much from a particular amount of benzene. So we got really 3 things going on there, but it'll help us put the concepts together. Okay, in this case, I've given you the equation for the reaction, burnt combustion of benzene. Benzene's a liquid at room temperature, and we're still going to produce carbon dioxide, and water. So those three things is the same for any combustion reaction. So I've copied their values again and copied in the value of the benzene. It's going to be calculated similarly to before, or at least at first. And so the standard heat of the reaction then is going to be 12 times the standard heat of formation for the CO2 plus 6 times the standard heat of formation for the H2O. That's my product side. Subtracting from that, it's going to be 2 times the standard heat of formation for the benzene, C6H6, plus 15 times the standard heat of formation for the O2. And that is my reactant side. And again, the O2 is going to go away because it's a free element. So let's work through all of that. So we're going to have 12 times 3, a negative 3, 93.5 kilojoules, plus 6 times a negative 241.8 kilojoules. That again is my product side. And I'm going to subtract 2 times my reactant side, which is 49.03 kilojoules. Then we're going to run all of that through our calculator. And when we do, we get a negative 6,270.9 kilojoules. Now that's not the answer to our question, but we needed it to get there. Because what it says is it wants it for 55.5 grams of this. This is how much would burn for 2 moles of benzene, not 55.5 grams necessarily. So we need to set up some dimensional analysis now with our 55.5 grams of benzene. Now it turns out, if you add up the molar mass, and I'll just give it to you for time's sake, 78.12 grams of C6H6 per 1 mole of C6H6. Again, that's just adding up the molar mass. Grams are going to cancel. And then we need another factor. We're going to use our heat that we just calculated, negative 6,270.9 kilojoules, which was our heat of reaction. But that was for 2 moles of benzene, so that's per 2 moles of C6H6, so that we get the proportions right. You run that through your calculator, you get a negative 2,230 kilojoules. So that's the amount of heat released when this mass burns. So it's specific to this amount of benzene.